Most people believe the eagle rules the sky through raw power. They imagine talons that crush and wings that dominate, a creature built for violence and supremacy. At first glance, this seems accurate. The eagle appears in heraldry and national symbols as the embodiment of strength, freedom, and conquest. What few realize is that the eagle's true advantage has nothing to do with force. Its dominance emerges not from aggression, but from precision, so refined that it borders on mechanical perfection. In a world where most predators rely on speed or stamina, the eagle has evolved to waste nothing. No energy, no movement, no opportunity. It is not the strongest hunter in the natural world. It is the most efficient. This efficiency begins with geography. Eagles do not choose their territories arbitrarily. They exist where topography creates vertical advantage. Mountain ranges, coastal cliffs, river valleys carved deep into plateaus. These landscapes channel air in predictable patterns, creating thermals and updrafts that rise like invisible highways through the atmosphere. An eagle positions itself not where prey is abundant, but where the physics of air movement reduce the cost of hunting to almost nothing. A golden eagle in the Rocky Mountains may patrol a hunting range of 50 square kilometers, yet spend less than 10% of its day actively flying. The rest is orchestration, reading wind, selecting vantage points, calculating trajectories before a single feather moves. The relationship between eagle and terrain extends beyond simple habitat selection. The bird does not merely occupy space, it reads it. Ridgelines generate predictable updrafts as prevailing winds collide with rock faces. Valley systems funnel air through narrow passages, accelerating flow and creating zones of turbulence bordered by streams of laminar air. An experienced eagle knows these patterns with the same intimacy that a river pilot knows currents and eddies. It positions itself in columns of rising air, circling without flapping, gaining altitude through physics rather than effort. On certain days, when atmospheric conditions align, a golden eagle can rise from valley floor to mountain peak, a vertical distance of 2,000 meters, without a single wing beat. The energy saved over a lifetime of such flights amounts to thousands of hours of active foraging time. The difference between survival and starvation in marginal territories. The habitat does not merely provide hunting grounds. It sculpts the predator itself. In open tundra, where prey is scarce and distances vast, eagles grow larger, their wings extending beyond 2 meters to maximize glide efficiency. In forested highlands, where maneuverability matters more than endurance, the same species develops shorter, broader wings capable of tight banking through canopy gaps. A bald eagle fishing along the Pacific coast has feet structured differently from one hunting rabbit's in interior deserts. The talons curve at angles calibrated to the shape and struggle patterns of its primary prey. Even feather density varies with altitude and temperature. An eagle at 4,000 meters carries more insulating down than one at sea level, yet both belong to evolutionary lines separated by fewer than 20,000 years. The environment is not a backdrop. It is a relentless engineer shaping bone density, muscle fiber composition, and neural processing speed across generations. The body that emerges from this process appears deceptively simple. Wings, talons, beak, components familiar to anyone who has seen a bird. But every dimension has been optimized beyond the obvious. Consider the wings. They are not uniform. The primary feathers at the wingtips spread like fingers, each one capable of independent adjustment to turbulence. These feathers twist and flex in response to air pressure Change is measured in fractions of a second, stabilizing flight in conditions that would tumble other birds into uncontrolled descent. The secondary feathers closer to the body generate lift with a curvature so exact that engineers study them when designing aircraft wings. The result is a flight profile that requires 40% less energy than a bird of equivalent size should need. An eagle can remain airborne for hours while expending fewer calories than a human burns walking the same duration. But the wing's sophistication extends deeper than aerodynamic efficiency. Each feather represents a point of data collection. Microscopic sensors in the feather follicles detect air pressure, velocity, and direction, transmitting information to the brain faster than conscious processing would allow. The bird does not think about adjusting its wings. The adjustments happen automatically, governed by neural circuits refined across evolutionary time. In turbulent conditions, an eagle's wings make hundreds of micro-corrections per minute, each one calculated and executed without deliberate thought. This is not instinct in any simple sense. It is distributed intelligence, where the boundary between brain and body dissolves into continuous feedback. The skeleton supports this efficiency through radical weight reduction. Bones are not solid but honeycombed, with air pockets, creating a frame that weighs less than the feathers covering it. Yet this apparent fragility conceals strategic reinforcement. The bones along the leading edge of the wing, where impact forces concentrate during prey strikes, are denser and thicker than those in the wing's trailing sections. The skull is double-layered with a cushioning space between, protecting the brain during high-speed collisions with prey. A golden eagle diving at a mountain goat may strike with force exceeding 15 times its body weight. The impact would shatter the skeletal structure of most animals. The eagle experiences it as routine stress, absorbed and distributed through a framework refined across millions of years. The musculature that powers this frame operates with similar precision. Flight muscles constitute nearly 30% of the eagle's total body mass, concentrated in the chest where their weight helps stabilize flight. But these muscles are not uniform tissue. They contain two distinct fiber types: slow twitch for sustained soaring and fast twitch for explosive acceleration. The ratio varies by hunting style. A fish eagle that ambushes prey from perches carries more fast twitch fibers. A golden eagle that pursues prey across open terrain develops more slow twitch endurance fibers. The body adapts to behavioral patterns, remodeling itself across seasons based on the demands placed upon it. The eyes operate on principles that seem to violate biological constraints. Each eye contains approximately 5 times the density of light, detecting cells as a human eye, over 1 million cells per square millimeter in the retina's central fovea. This allows resolution so acute that an eagle soaring at 3,000 meters can distinguish a rabbit from a similarly sized rock based on the texture of its fur. But density alone does not explain the advantage. Eagle eyes contain 2 foveas per eye rather than one, creating dual focal points. One fovea provides forward binocular vision for tracking prey during pursuit. The other, positioned laterally, maintains monocular coverage of the periphery for threat detection and navigation. The eagle sees forward and sideways simultaneously, processing both image streams without confusion or delay. The optics supporting this vision system approach the theoretical limits of biological possibility. The cornea and lens focus light with minimal chromatic aberration. the distortion that plagues even sophisticated camera systems. The depth of field adjusts instantaneously as the bird shifts attention between distant and near objects, a feat that requires complex muscular control of lens shape. Perhaps most remarkably, the eagle's visual system compensates for its own motion. During flight, the head remains stable while the body pitches and rolls beneath it, maintained by vestibular reflexes operating faster than conscious correction. The result is an image stabilization system that rivals modern camera gimbals, allowing the eagle to track a fleeing rabbit while banking through turbulent air color perception, extends into ultraviolet wavelengths invisible to humans. This reveals patterns in fur and feathers that prey animals use for camouflage against mammalian predators. A ptarmigan hiding in snow appears perfectly concealed to a fox. To an eagle, the bird's plumage reflects ultraviolet light in distinctive patterns that stand out against the snow's uniform UV signature. The advantage extends beyond detection. Urine trails left by rodents glow under ultraviolet light, marking the pathways and territories of animals that believe themselves hidden. An eagle hunting voles does not search randomly. It reads a landscape illuminated by chemical signatures, identifying active burrows and travel routes before committing to the hunt. But vision alone does not explain hunting success. The eagle integrates multiple sensory streams into a unified model of its environment. Hearing, though less acute than in owls, still detects prey movement in tall grass or beneath snow proprioception. The body's sense of its own position operates with extraordinary precision, allowing the bird to gauge wind speed and direction through pressure sensors in its skin and feathers. Even the inner ear contributes, providing three-dimensional orientation data that prevents disorientation during complex maneuvers. These systems do not operate in isolation. They feed into a neural architecture that constructs a real-time spatial map, updating it continuously as conditions change. The mechanics of a hunt unfold with economy that borders on indifference. An eagle does not chase. It positions from a cliff edge or thermal current. It scans terrain while expending minimal energy. The waiting is not patience in any emotional sense. It is calculation. The bird tracks wind direction, sun angle, and prey movement patterns, assembling a geometry of interception. When conditions align, the descent begins not as frantic pursuit, but as controlled fall. The wings fold partially, reducing drag. The body angle adjusts to terrain contours, using gravity rather than fighting it. Speed accumulates without effort, 80, 100, 120 kilometers per h-hour until the final moment. During this descent, the eagle's visual system performs calculations that would challenge sophisticated computers. It tracks the prey's velocity and direction, predicts the intercept point, and adjusts its own trajectory to arrive at that point simultaneously. But the prey is not static. A rabbit fleeing into brush does not run in straight lines. It dodges, changes direction, seeks cover. The eagle compensates in real time, making constant micro adjustments to maintain the intercept solution. The margin for error narrows with each second. At the moment of strike, the eagle must be at the exact three-dimensional coordinate where the rabbit will be, moving at the correct angle and speed. Miss by centimeters, and the hunt fails. The precision required is staggering, yet eagles succeed more often than they fail. The strike happens faster than conscious reaction, allows talons extend a fraction of a second before impact, toes spreading to maximum span. Each talon curves to a point sharper than most surgical instruments, driven forward by leg muscles capable of exerting crushing pressure exceeding 200 pounds per square inch. The impact is not random stabbing. The rear talon, longer and more curved than the others, pierces vital areas with anatomical precision. The base of the skull in birds, the spine behind the shoulders in mammals. Prey animals die from trauma or severed circulation within seconds. The eagle does not wrestle or struggle. It calculates the killing blow and executes it, then waits for stillness before feeding begins. But not all hunts succeed through power. Some eagles employ strategies that reveal cognitive complexity, difficult to reconcile with instinct alone. Golden eagles hunting mountain goats in alpine terrain have been observed driving prey toward cliff edges, not through direct attack, but through calculated positioning. The eagle does not strike the goat. It flies at the goat's head repeatedly, forcing the animal to rear and sidestep. Each retreat moves the goat closer to the precipice. When the animal finally loses footing and falls, the eagle follows the descent, waiting for the impact below. This is not opportunistic scavenging. It is geometry weaponized, using terrain as a tool when direct predation would fail. The behavior suggests more than simple stimulus, response conditioning. The eagle must understand that cliff edges represent danger to goats, but not to itself. It must recognize that repeated approaches will drive the goat in a predictable direction. It must maintain the strategy across minutes of activity, resisting the urge to strike directly, even when the goat appears vulnerable. This requires planning across multiple steps, inhibition of immediate impulses, and understanding of causal relationships between action and outcome. Whether this constitutes true cognition or merely complex instinct remains debatable. What is certain is that the behavior works, and that eagles who employ it access food sources unavailable through conventional hunting. Similarly, pairs of eagles hunting together do not cooperate through instinct alone. One bird flushes prey from cover, while the second positions downwind, anticipating the direction of flight. The roles reverse on subsequent hunts, suggesting awareness of tactical variation rather than fixed behavioral patterns. The coordination requires each bird to track not only the prey but also its partner's position and likely actions. This is joint attention, the ability to maintain awareness of what another individual perceives and intends. It appears in few species outside of primates and corvids, yet eagles demonstrate it routinely during cooperative hunts. Young eagles learning to hunt do not perfect these techniques immediately. They fail repeatedly, misjudging distances and angles, burning energy on pursuits that yield nothing. Efficiency is not inherited. It is learned through iteration, refined across seasons until waste approaches zero. A juvenile eagle in its first winter may succeed in only one hunt out of 10 attempts. An experienced adult may succeed in 7. The difference is not physical capability. Young birds are often stronger and faster than adults. The difference is judgment, accumulated through thousands of hours observing prey behavior, testing approaches, and integrating feedback from successes and failures. The daily rhythm of an eagle's life resists romanticization. There are no dawn patrols driven by majesty or sunset flights tinged with meaning. The bird wakes when body temperature and light conditions make flight metabolically favorable. It hunts when prey is active and wind conditions allow efficient travel. It rests when neither condition is met. A bald eagle along a salmon river may feed intensively for 3 weeks during the spawning run, then fast for days when fish populations recede. The body stores fat reserves during abundance, then metabolizes them during scarcity. Weight fluctuates by up to 15% across seasons. This is not feast and famine. It is calibrated response to predictable resource variation. Between hunting periods, eagles spend hours in activities that appear idle but serve essential functions. Preening maintains feather structure, realigning the microscopic barbules that give feathers their aerodynamic properties. A damaged feather can reduce flight efficiency by several percent, seemingly trivial, but sufficient to mean the difference between successful pursuit and failure. Feathers are not living tissue. Once grown, they cannot repair themselves. Maintenance is the only option, and eagles invest time proportional to the stakes. Primary flight feathers receive attention multiple times daily. Secondary feathers less frequently. Down feathers, important for insulation but not for flight, receive minimal maintenance except before extreme weather. Bathing serves similar functional purposes. Eagles bathe not for comfort, but to maintain feather waterproofing and remove parasites. The process follows a precise sequence, wading into shallow water, dipping the body repeatedly, then retiring to a sunny perch for drying. The drying is not passive. The bird positions itself to maximize sun exposure, spreading wings and tail to expose maximum surface area. In cold conditions, a soaked eagle faces real danger. Wet feathers lose insulating properties and increase weight. The bird cannot hunt effectively until dry. A miscalculation in bathing timing can cost half a day's hunting opportunity. Seasonal migrations, where they occur, follow routes determined by wind patterns and prey availability, rather than destination preference. A juvenile golden eagle leaving its natal territory in autumn does not navigate toward a specific location. It follows thermal corridors southward until reaching regions where snow depth remains shallow enough to expose prey. Some individuals travel 3,000 kilometers. Others move less than 200. The distance is not predetermined. It is a function of where conditions stabilize. Young birds that miscalculate, pushing too far into regions where competition is high or returning too late to claim territories, die at rates exceeding 50% in their first year. Migration is not journey. It is risk calibrated against necessity. The navigation mechanisms eagles employ during migration combine multiple cues. Magnetic field sensitivity, mediated through specialized cells containing iron crystals, provides a compass heading. Sunday position offers directional information compensated for time of day through an internal clock. Landmarks, memorized during previous travels, provide local navigation references. In overcast conditions, when visual cues disappear, eagles rely increasingly on magnetic and olfactory information, detecting gradients in atmospheric chemistry that mark geographic features like coastlines and mountain ranges. No single system is sufficient. Redundancy is the strategy. Multiple overlapping cues ensure navigation continues, even when specific information sources become unavailable. Breeding territories reveal hierarchy enforced through persistence rather than combat. Established pairs occupy cliff nesting sites that may have been used for decades, sometimes centuries. These locations are not random. They provide shelter from weather, proximity to hunting grounds, and visibility across wide territories. A pair defending such a site does not fight rivals directly unless forced. Instead, they patrol boundaries, vocalize from prominent perches, and dive at intruders who venture too close. Most challenges end without physical contact. The energy cost of territorial combat is too high to justify, except in cases where no alternative exists. Young eagles seeking to establish territories spend years probing for weaknesses, waiting for the death of an established bird before claiming the vacancy. The displays used in territorial defense follow ritualized patterns designed to communicate capability without requiring actual combat. An eagle defending territory might fly to maximum altitude, then dive at extreme speed past an intruder, pulling up meters away. The message is clear: the defender possesses the skill and energy to pursue this intruder anywhere, at any time. Most intruders withdraw rather than test the claim. Those that do not withdraw face escalation. The defender closes distance, making contact with talons but not gripping, a warning rather than an attack. Only if this fails does actual combat begin, and even then, both birds usually disengage before serious injury occurs. The fitness cost of injury is too high for either bird to risk, except in defense of essential resources. The nest itself becomes an architectural statement of tenure. Each breeding season, the pair adds new material, branches, grass, moss, until the structure reaches masses exceeding 200 kilograms. Some nests grow large enough to collapse the trees supporting them. The size serves no functional purpose beyond signaling occupancy. It is investment made visible, a declaration that the territory is held and will remain held. Eggs are laid in late winter or early spring, timed so that hatching coincides with peak prey availability. The female incubates while the male hunts, delivering food at intervals determined by chick demand. The process is not affectionate. It is transactional energy converted to offspring viability. Incubation requires constant vigilance. Eggs must be maintained within narrow temperature ranges. Too cold and development ceases. Too warm and the embryo dies. The female turns eggs regularly, preventing the developing embryo from adhering to the shell membrane. She regulates temperature through precise positioning, covering eggs completely in cold weather and shading them in heat. During brief foraging absences, she covers eggs with nest material for insulation. The male, though he may occasionally take brief incubation shifts, spends most daylight hours hunting. The demands are severe. He must provide not only for himself, but for a female whose mass increases during egg production and who cannot hunt while incubating. In territories where prey is sparse, males may hunt from dawn to dusk, traveling 50 kilometers or more in a single day. Sibling dynamics within the nest expose the absence of sentimentality. When food is abundant, all chicks survive. When prey is scarce, the largest chick, usually the first hatched, monopolizes feeding. Smaller siblings weaken, then die. The parents do not intervene. They deliver food and depart, indifferent to the allocation. This is not cruelty. It is optimization. Raising one robust chick offers better genetic prospects than dividing resources among 3 weak ones. The system favors survival probability over fairness. By fledging age, the surviving chick has consumed biomass equivalent to hundreds of rodents or dozens of fish, resources extracted from a landscape where nothing is surplus. The development of hunting skills in young eagles follows a trajectory measured in years, not weeks. Fledglings leave the nest capable of flight, but not of hunting. They spend weeks following parents, begging for food, while practicing the mechanical components of pursuit. They dive at inanimate objects, sticks, grass clumps, shadows, developing the neuromuscular coordination required for controlled strikes. They attempt hunts and fail, learning through failure which prey species are vulnerable and which are not. A young eagle might attack an adult rabbit and discover that the prey's strength and aggression make capture impossible. The same eagle will later learn to target juvenile rabbits whose coordination and strength have not yet developed. This is not instinct. It is learning, trial and error extended across seasons until success rate climbs toward viability. The eagle's role within its ecosystem resists simplification into predator-prey binaries. It does not control populations through predation alone. Its presence alters behavior across trophic levels. Rodents in territories patrolled by eagles shift activity patterns toward nocturnal hours, reducing daytime exposure. This behavioral change cascades. Vegetation that would have been grazed during daylight grows unchecked. Seed dispersal patterns shift. Insect populations feeding on those plants fluctuate. The eagle does not intend these effects. They are emergent properties of a system responding to predation pressure. Scavenging introduces further complexity. Bald eagles along coastlines consume more carrion than live prey during certain seasons, feeding on fish that died of natural causes or marine mammals washed ashore. This scavenging prevents nutrient concentration in localized decay sites, redistributing biomass across wider areas. Golden eagles in winter feed extensively on carcasses of ungulates killed by cold or starvation. By accessing these resources, eagles reduce competition for live prey among other predators, indirectly stabilizing populations of foxes and coyotes that might otherwise face resource bottlenecks. The scavenging role also connects marine and terrestrial ecosystems in unexpected ways. A bald eagle feeding on salmon carcasses along a river accumulates nutrients derived from the ocean. When the eagle later dies in an inland territory, those ocean-derived nutrients enter the terrestrial soil through decomposition. Over decades, thousands of eagles transport tons of marine nutrients into forests and grasslands, enriching ecosystems that would otherwise remain nutrient poor. The eagle functions as a biological pump, moving resources across boundaries that would otherwise remain separate. Human presence in eagle territories appears most often as disturbance rather than threat. Agricultural development fragments, hunting grounds, replacing grasslands and forests with monocultures that support fewer prey species. Pesticides accumulate in prey animals, concentrating in eagle tissues and thinning eggshells to the point of collapse. Power lines crossing migration routes kill hundreds of eagles annually through electrocution. Wind turbines positioned on ridgelines, the same thermal corridors eagles use for efficient travel, turn flight paths into hazard zones. These impacts do not result from malice. They emerge from human systems designed without consideration for consequences beyond immediate function. Some eagle populations adapt. Bald eagles now nest in urban parks, fishing in lakes bordered by jogging paths and playgrounds. Golden eagles in Spain hunt near highways, exploiting roadkill as supplemental food sources. These adjustments suggest behavioral plasticity, yet they come with costs. Urban eagles face higher parasite loads from waterfowl concentrated in limited habitats. Roadside hunters risk vehicle strikes. Adaptation is not triumph. It is compromise imposed by constrained options. Conservation efforts, where successful, operate through habitat protection rather than direct intervention, restricting human activity near nesting sites during breeding season allows pairs to reproduce without disturbance. Removing DDT and similar pesticides from agricultural use permits eggshell recovery. These measures do not save eagles in any heroic sense. They remove specific pressures, allowing populations to stabilize toward historical baselines. The eagle's recovery is not a human gift. It is the removal of human burden. standing beneath a cliff where eagles nest, watching an adult return with prey clutched in talons, it becomes possible to mistake presence for meaning. The bird does not see the observer. It registers potential threat, evaluates distance and behavior, then proceeds with feeding if risk appears minimal. There is no acknowledgement, no connection. The eagle exists in a continuum of wind, hunger, and territory that preceded human observation and will continue regardless of it. What seems like grace is physics. What appears as power is efficiency refined across epochs. The eagle does not symbolize freedom because it flies. It flies because flight offers the lowest energy cost for accessing dispersed resources across vertical terrain. It does not embody nobility through hunting prowess. It hunts with precision because inefficiency leads to starvation in environments where prey is sparse and competition is constant. The meanings humans assign to eagles, courage, vision, dominance, are projections onto an animal governed by metabolic requirements and environmental constraints. Yet, something persists beyond the mechanics, not meaning in any anthropomorphic sense, but a form of coherence. The eagle exists as a solution to specific problems posed by its environment. Every feather angle, every visual receptor, every hunting strategy represents an answer tested across millions of iterations. The animal is not beautiful because it inspires awe. It is functional to a degree that transcends utility, achieving a form where nothing is extraneous and everything serves survival. This is not design. It is attrition, the gradual erosion of everything that does not work, leaving only what remains. In this sense, the eagle offers no lessons. It makes no claims about how life should be lived or what values should guide action. It simply continues, bound by principles older than language or consciousness. To watch an eagle hunt is to witness a transaction between organism and environment, stripped of narrative or intention. The bird calculates, strikes, feeds, and rests. The cycle repeats until it ends. Nothing in this process invites human participation or validates human perspective. Perhaps this is why eagles command attention, despite their indifference. They function in a realm where human concerns dissolve, where survival is measured in calories expended versus calories obtained, where success is simply continuation and failure is silence. The eagle does not care if it is observed or admired. It cannot afford to. Every moment diverted from the essential tasks of survival is a moment subtracted from the narrow margin that separates persistence from extinction. Beneath the symbols and the metaphors, this is what remains: a predator shaped by altitude and wind, equipped with tools inherited from ancestors who faced identical challenges across unimaginable spans of time. The eagle does not rule the sky. It occupies a niche defined by physics and biology, exploiting resources with precision that borders on perfection. In a world increasingly shaped by human intention and intervention, it endures as a reminder that some systems operate beyond control or comprehension, not because they are mystical, but because they are governed by principles indifferent to observation. The cliff falls silent as the eagle departs, wings spread against thermals rising from the valley below. There is no farewell, no acknowledgement of passage, only movement, efficient, calculated, and utterly without waste. The sky receives the bird as it always has, as it will continue to do long after the observers below have turned away. What remains is not inspiration or meaning, but fact. In this place, at this moment, the eagle survives, and survival stripped of everything else is enough. From the heights of the mountains to the open sky, the eagle remains a symbol of adaptation, patience, and balance. Every creature has a story, and this was the story of the eagle.